Okay, cool. I guess I'll probably just get started then, because we're gonna have a lot to get through with this one. Um, I'm hoping we're able to get through two implementations of type checkers, uh, but we'll get into that. So I guess just to kind of introduce myself, start us off. My name's Kevin Wilde. I'm a front-end engineer at Course Hero, and in this workshop today, we're going to be working on implementing a static type system for a simple programming language. Um, so like I mentioned a couple minutes ago, hopefully you were able to find this GitHub repository. Um, but otherwise, again, just go to my GitHub page, which is just my name. And then this repository will be the first pinned repo there. And go ahead and just follow these three instructions. Once you've done that, there's some more information here in the README. I've added just a couple commands. We're mostly going to be running this test command when we're implementing the type checker and running the test to verify that we've done it correctly. If you try to run this right now after cloning the repo, you should see a whole bunch of errors that all say to do. So that's because we haven't implemented anything yet. We're going to be filling in that implementation so that hopefully we can get those tests to pass. The overall format of the workshop today, I'm going to spend hopefully about like 25 minutes giving an overview of the programming language that we're building. This will cover things like the grammar and syntax and so on, so that everyone's like up to speed on and has the required knowledge of the language in order to actually implement the type checker. So I know that that first part is going to kind of be a big chunk of me just sort of like talking, but we just gotta, like I said, get everyone kind of up to speed so that we can get into writing code. So then the next, hopefully 25 minutes will be a type checker that relies on type annotations, meaning that the programmer who's writing in this programming language will have to say like when it expects something to be an int, when it expects something to be a string, etc. After we finish that one, then we're going to move on to discussing type inference and how that type inference algorithm will work. And then the bulk of the time in the second half of the workshop will be actually implementing that type checker with inference. And then finally, I just wanted to note down here that I have these like checkpoint links here. So everything that we're implementing in this workshop is like already available in different branches on this repo. So if you're following along and at any point you like need to reference something or you miss something at any point, you can use these to kind of refer back to those things. But I would recommend not looking at them right now because they're kind of like the answer key. These are the implementations that we're going to be doing during the workshop. Okay, so yeah, with that said, I guess we will get right into it. So I'm going to start with this kind of introduction to like the programming language implementation. So the workshop today, we're going to be focused on just this type checker portion of the language. But let's kind of just go through an overview of kind of the language and the pieces that make it up from like beginning to end. So the programming language that we're building consists of four pieces. So there's the lexer, the parser, the type checker, and the interpreter. So the lexer is the thing that takes the source code as input and produces a sequence of tokens. So it's taking the actual string of the like source code file and transforming that into a sequence of tokens. And I'll explain what exactly tokens are in just a moment. The parser consumes that sequence of tokens that's produced by the lexer and then produces an abstract syntax tree, or AST. And again, I'll explain in just a minute kind of what exactly goes into this abstract syntax tree. The type checker then consumes that AST as input, and it will either succeed or fail. If it succeeds, then the interpreter will take the AST that was produced by the parser and evaluate it and just kind of, return the result or print the result. So this is pretty much, this is just kind of, this code is actually pretty much what you'll find in the index file of the repo. So we'll just take the program, which is the source code, as a string, pass that to the lexer. We'll then pass that lexer into this create AST function from our parser. Once we get back that AST, we'll type check it and just kind of ignore the result because we're going to just have the type checker throw an error if it runs into any issues. So if it throws an error, it'll fail with a type error. If we don't have any error, then we just pass that AST into this evaluate function from our interpreter and print the result. Okay, so let's go into the specific grammar for our language. So I mentioned in the previous section tokens that are produced by the lexer and terms which are in the abstract syntax tree. So in our language, every program that we're writing will be a single expression. And that probably sounds very restrictive, but we'll actually be able to write pretty interesting programs with that single expression just by kind of nesting these expressions as we'll get into here. So the grammar for our language is specified here. And I'm going to go over this really quickly because I think it'll actually be easier to look at this table with examples. So an expression can be, we have booleans, ints, strings. We also have an ID. That just means like a variable or a function name. It could be a standard library function or a function you've defined. But that's just, any sequence of characters that doesn't have white space in it. We have and expressions, which take two expressions to them and do what you'd expect. We have or, we have if, which has the condition, the then expression, and the else expression. Empty is a keyword that signifies the empty list. Cons is how you create or add things to lists. So this is the thing you're adding to the list, and then this should be an existing list. Let expressions are how we will define variables. So you'll say let, you'll say an ID like X, the value that you're assigning to that ID, and then the body of the let expression where you can refer to that variable you've just defined. Lambda is a keyword that allows us to define a function. It's followed by this inside parens. You'll have a sequence of parameters that your function expects. So again, this could be like X and int, or Y and string, whatever, and then the body of the function where you can refer to those parameters. And then this is how you call a function. So you open paren, and then this first expression should be a function, and then the remaining ones are arguments that are being passed to that function. So that was really fast. We'll look at some examples here, which I think will make it a little clearer. So for the Boolean case, there's two examples really. This is how true is represented, and this is how false is represented. Int is what you'd expect. String, anything that's inside double quotes. ID, like I said, this is just kind of variable names, function names, etc. And it's any sequence of characters that doesn't contain white space. So you'll notice we can even do like hyphens in the variable names. Plus, in this case, will be a function in the standard library. String concat is also in the standard library. Empty tells you whether a list is empty. That's in the standard library. And you'll notice this question mark, again, any sequence of characters that doesn't have white space, or parens, I guess, since we're using parentheses for as tokens in our language. Okay, and expressions. There's two sub-expressions which are passed to and, which should both be Booleans. So and true and false would be false, of course. This is going to say and x is greater than 1 and x is less than 5. Or is similar. If has three sub-expressions. So again, the first one is the condition. Then we have the then expression. And then we have the else expression. So this one says if true, return 1, else return 0. So this would evaluate to 1. And this one is if x is less than 10, return small, otherwise big. Empty is a keyword that just signifies the empty list. Cons is how you add something onto a list. So this first one would create a new list which has one int inside it, the number 1. This one has two ints. It's a list of two ints, 2 and 1. And this one is a list of strings. Let expressions are how we define new variables. So this one is let x be 1. And then in the body, we can refer to x. So then we are saying x plus 1, which would be 2. Here again, let x be 2, and then we're just creating a list of that. Lambda is the keyword for defining functions. So this first one creates a function which accepts one argument and expects it to be an int, and then returns x plus 1. You can accept multiple arguments by just separating them with spaces. So this second one here accepts 3 arguments, and just if the first one is true, then it returns y, otherwise it returns z, and so on. This third one, you can see we're nesting this if expression. So if x is greater than 0, we say positive. Otherwise, if x is equal to 0, we say 0. Otherwise, negative. And then finally, this last one, when you see an open paren, that means we're going to be an open paren that's not followed by like one of the keywords we've just gone through. That means we're calling a function. So again, plus is a function that's in the standard library. So when you're seeing something like this, that means we're calling the plus function, and we're passing x as the first argument, 1 as the second argument. And these examples are examples where we're calling a function that we're defining. So we've defined this function, which adds 1, and then we're calling it with 42. And we've defined this function, which adds its arguments, and we're calling it with 42 and 43. And then here's an example that has a few things together. So we have a let expression where we're creating this variable called multiply by 2, and we assign it the value of this function. So this would be like similar in JavaScript to if you said like var multiply by 2 equals function x times 2. And then down here is where we're calling it. So this highlighted portion is what is matching this case of our grammar. So the grammar above is the complete grammar, but I want to point out that there are additional rules that need to be enforced by the type system. So the examples in the table above are all well-typed programs, meaning that they conform to the grammar as well as the typing rules. But it is possible to write a program that satisfies the grammar and still has a type error. So some examples of rules that must be enforced by the type system are things like, when you have an ID like x, that has to refer to a variable which is in scope. The two arguments that are passed for and or expressions must both be Booleans. The second argument for cons has to be like the same element type must have the same element type as the first thing you're passing, or be the empty list, and so on. So just some examples of programs that satisfy the grammar but have a type error are things like if you just say x, if this is the entire program, x has not been defined, so it's not in scope. This would be a type error. If you try to pass an int to and, that's a type error, or a string for or, that's a type error. If you try to have different types for your then branch and your else branch, that's going to be a type error. This is expected to be a Boolean. So if you try to pass an int as the conditional, that's a type error. Here we're trying to cons an int onto a list of strings. So that's a type error. The wrong number of arguments are being passed to this function. It takes only one argument, x, and we're passing 2. And finally, this expects the argument to be an int, and we're passing a string. Okay, so with that grammar defined, we can now say exactly what the tokens and terms in our language will be. So the tokens, I'll go over quickly, but you don't have to, you won't have to deal with these too much in your actual implementation, because you'll recall that the tokens are produced by the lexer and consumed by the parser. And so the type checker, which is what we're going to be working on, will not actually be dealing directly with these tokens, but I'll just go through them real quick. So the parentheses are tokens. Colon is a token because we use that for the type annotations. Arrow is a token, which is for when you're putting a type annotation for a function type. Let is a keyword. If, and, or, lambda, and empty. These are all keywords. And then Boolean, which has a value, int, which has a value, and string, which has a value. So like if you see the token, or if you see in your actual source code, you see like the number 42, that would be an int token with the value 42. And then the last one is ident, which stands for identifier. That's like the ID case I've been mentioning. Any sequence of characters not separated by white space. So it has a name, so that would just be like X or Y or my variable, whatever you call it. Okay, let's go through the terms then. So these are more important for us because again, the parser is consuming the sequence of tokens and then producing an abstract syntax tree where the nodes are going to be these terms. So these terms are what is going to be passed into our type checker. So, and I just want to point out, since we went over this grammar before, and it had these different cases, this is going to line up pretty much one-to-one with the cases that we have in our grammar. So again, we have a term for Booleans, which has a value, int, string, variable, which has a name. We have our if term, which has 3 subterms, the conditional, the then, and the else. Our let term, which has the name of the variable we're defining, and then the value and the body where it can be used. We have empty. We have our cons term, which has 2 subterms. This is the thing you're adding to the list, and then this is the existing list. Those are called car and cdr. That's just like a functional programming thing. I don't even remember exactly why that is. I learned it at one point, but I've forgotten, and it's not super important. This is just like car is the first argument to cons, and then cdr is like the second one, the list that you're adding to. This is our term for function abstractions. So when you create a function that's going to create a function abstraction term, it has a list of params. Each param has a name and a type annotation, and then it has the body of the function. And then finally, we have our term for function calls or function applications, which has the function that you're calling, as well as an array of arguments that you're passing to that function. And then the types here are, again, just we have Boolean, int, string. We have a type for lists, which has a subtype. Like this would be, list of int. It could be list of string. It could even be like list of int. And then we have our arrow type, which is the type that describes a function, which has an array of parameter types and a return type for the function. You may have noticed I said this corresponded like one-to-one with this grammar. You may have noticed I skipped and or, and that was done because both of those expressions can be translated into an equivalent if expression. So, specifically, kind of what you expect, and x bar 1, x bar 2 is equivalent to if x bar 1, then x bar 2, else false. And kind of a similar idea for or. So the reason to do that is just it makes it more convenient for the programmer. They can write ands and ors, but our type checker and interpreter only have to handle the if expression and doesn't have to even be aware of and or. So we've kept things simpler for ourselves and have to handle fewer cases while still providing and or in the language. And just one example to kind of hammer home how these terms are going to be like the nodes of our abstract syntax tree. So because the terms, you saw that they kind of refer to themselves, like they have subterms inside, that's what makes it into a tree. So if we have something like this, you'll see that this overall, the root node of the tree is a function application. Again, that means function call. The function that we're calling is here, and the arguments we're passing are here. So the function we're calling takes two arguments, x, which is an int, and person, which is a string. The body of the function is an if term, and the conditional of the if is a function call that checks if x is greater than 0. The then branch is another function call, which would return string concat of hello and the variable person, which is, again, whatever was passed into this function. And the else term is the string goodbye. And then the arguments that we're passing into the overall function are 1 and Kevin. So the source code for that AST would look something like this. We have the open paren and close paren. So we're calling a function. The function we're calling is here, and we're passing 1 and Kevin. And again, by the way, the greater than is in the standard library, and string concat is also a function in the standard library. So this would evaluate to hello Kevin because 1 is greater than 0, so we take this branch. Okay, with all that said, we're gonna jump into our implementation now. So again, in this workshop, I'm hoping to get through two implementations. This first one that we're gonna do is a type checker that relies on type annotations. So specifically, when you have a function here, you have this type annotation which says x is an int and person is a string. So yeah, I guess let's just get into that then. So if you're following along, you can start on this branch 0, 1, no inference start point, and open the type checker file. So I'm going to switch over to the code now. I'll close this. So all the code that we kind of talked about is here. So there's the lexer, there's the parser, type checker and interpreter. You also find like the standard library and so on. But we're going to be working in this type checker file. So I have the type that we went over before, booleans, int, strings, lists, and arrow type, which is, again, functions. I've commented out the list type for now, and we're gonna come back to that one later. So just for now, we're gonna kind of skip that and come back to it later, and I'll kind of explain why and talk about it at that point. So our type check function, again, you'll remember from here, the type check function is going to consume this AST. The root node is a term that we've been going over, and we'll have it return the type of the program. So given that we are taking this term as an argument, we know that the term can be any of those cases that we were looking at before, Boolean, int, string, etc., the if expressions, let expressions, and so on. So what we're going to do is have a switch statement that looks at this term's tag, and then just have a different case for each each possible value of this term. So I've kind of pre-filled that in here just so you don't have to watch me type out all the possible terms. And then this default, this assert never is just like a TypeScript thing that I'm doing here, which just checks that we've handled every possible value of term.tag. So like if I comment out one of them, then it's going to complain at me and tell me I haven't handled Boolean. Okay, so this is kind of the like backbone of our type checker here. And now we just have to fill in the cases for each type of term. So the first three are going to actually be quite simple. It's not a trick question. If you're given a term that is a Boolean, what is its type? Well, this one is pretty trivial. A Boolean term has the type Boolean, and that's it. Ints are just as easy. This will be type int, and strings are similarly easy as well. All right, so 3 of them down. Now we hit variable. So you'll recall that the term here just has a name. So this would just be like X or something. So just based on the name alone, there's nothing like there to tell us what the type of that variable is. So we need to like kind of keep track of what variables have been defined so far in the program and what types they have. So the ways to define a variable are with let expressions or with a function abstraction, because when you have a function which takes like a parameter x, then in the body you can use the variable x. So we know that in each of these cases is where variables are introduced. So we can just kind of, within these cases, we'll do something to kind of keep track of those variables. We'll, add them to some list or something. And then here we can kind of just, what we want to do is just sort of like look up, see if this variable exists and what type it has. So for now, I'm going to just kind of say that we're just going to like get the type of this variable from the kind of I'll call it the context because I've seen other people call it that. And we'll pass the name of the variable that we're trying to look up and then some context that we have to define here. So I guess first let's decide on what this context is actually going to be. So I said we needed to keep track of, well, we need the name of each variable and we need to know its type so that we can, now in this function, look up its type. So I guess I'll just say that the context is going to be, let's just say it's an array and each entry is going to have the name and the type. So nice and simple, just an array where each element is of this shape. So you can probably, you can imagine this is maybe not the most efficient implementation because we're just going to iterate over this array to try to find this name inside it. But it's nice and simple. It'll work well for us. And actually, one of the nice properties here is that this will actually help with like, if you try to shadow a variable. So if you do something like, say let x be 1, and then in the body here, you say actually let x be 2, and then you say, x plus 3. This should return 5 because this x here is gonna shadow the first x. So by having this be an array, we'll get that like pretty much for free by just, we can add things at the front of the array. And so then when we try to look up that name, whichever x we find first is the most recent definition of x. And so that'll kind of handle that shadowing for us. So that'll be our context type. So I'm not sure exactly what we want context to be here yet. So I'll just say, for now, we'll start with it as an empty array in here. And we can write this function for now. Hit type from context, it takes the var name, which is a string, and it takes a context. And then we are just going to basically, say context.find item where item.name equals var name. If we find it, we'll return its type. Otherwise, we will throw an error and say undefined variable. Okay. Let's do if expressions then. So if expressions or if terms have 3 subterms, so we can say we'll get the con type, and we can get that by just recursively calling this function and passing the cond in. We can get the then type by passing term.then, and we can get the else type with this. And then what we're going to do is just say, well, the con type has to be type Boolean. If it's not, we'll throw an error. Type bool for cond. And then we need the else type to match we need the then type and the else type to match. And if they don't, we'll throw an error. If those things are satisfied, then we can just return either the then type or the else type. They're the same, so it doesn't matter. The overall result will be one of those branches. Okay, so that handles if. Now let's do let. So this is where we're going to define a new variable. So what we can do is say the val type is, if we type check term.val, that'll give us the val type. And now we want to add that to the context. So we can say, maybe we'll try this and say context.push term.name, and type is going to be val type. And then we want to say type of the body is going to be type check term.body. Okay, so we're pushing to the context here, but then when we call type check on the body, it's just going to come up here and kind of create its own context variable that's empty, right? So we need we want this context to be the one, we want this call to have access to this context. So what we have right now won't quite work. We could maybe try moving this up and making it like a global variable inside this file. And that way, this call would still reference the same thing. But the issue with this is that this will make things difficult to manage the scope of variables. So again, if we do something like this, and we say let y be 2 and then add y3, but let's say this was an addition call, and we want to add, so we want to add the result of this, which is going to be 5, to 42 or something. Well, so right here, this works fine. We have y be 2, y plus 3, which is 5, and then we're going to add that to 42. But if we replace this with y, the scope of the y variable should only be for the body of this let expression, and we should not be able to refer to it here because we're outside of the let expression. So if we just have this global, array, once we put something in there, then it would be available anytime after that, and everything would be referring to that same array, which would make things, it wouldn't be possible then to have scoped variables which are, available for this body but then not available afterwards. So what we can do instead is we want this to be an argument to this function. But we also, at the same time, we need to do this without changing the interface that's expected here, because this is just going to pass, it's just going to give us the AST. So what we want to have is this context available as an argument. So what we can just do is, well, we can just kind of go ahead and do what we want it to be, which is this function will take the context, and this one won't be exported. This will just be kind of our helper function. And the one we export will have the correct interface that's expected, outside of this file. So I'll rename this here, and I'll just call this type check. Well, I'll just call it type check helper for now. We can maybe fix that later. And this exported function is just going to return whatever that returns, passing through this term. And it needs to pass the context, which initially will say nothing has been defined, no variables have been defined. So initially the context is just empty. And so now we don't need this global variable here either. Okay, so now I just need to, in each of these places, pass that context through. And instead of pushing to the context here, because that would mutate the context, instead of doing that, I'm going to just say, make a new context. And what I'll do is add that at the front, like I said, so that that handles variable shadowing, and spread the old context onto the end. And then we'll pass that new context when we're getting the type of the body. So that way the body is able to refer to any variables that, or in this case, the one variable that the let expression has bound. And once we evaluate that, we can just return body type as the type of the overall let expression. Okay. So now let's do function abstractions. So what we have here is, again, this is another way to introduce new variables that can be referred to within the body. So we're going to actually do something quite similar, which is going to be like param context, and we'll just say term.params map over each of those, and this is going to be just the param name, and then the type is going to be, so the params in this version of our language must be annotated with their type. So that's just the type annotation, param.typean. And once we have that, then the new context is just, we can spread that param context, we can spread the old context, that gives us the new context, and then body type, again, is type check helper, passing term.body, and the new context so that it can refer to any of those params that are taken by this function. And then, well, we actually don't want to return body type here, right? So the term is a function, and the body is the thing that function returns. So this function could be, like the add one function that takes x and returns x plus 1. So body type would be int, because x plus 1 is an int. That's the return value of the function. The overall type of the function itself is this arrow type that we've said. The param types are, well, again, we can just say term.params dot map each param to its type an, and then the return type, this is the body type, right? So that handles our function abstraction case. And our last one here is function applications, or function calls. So we have two subterms or two things to deal with here: the function and the arguments. So we can get the function type by, again, just recursively calling type check helper on term.func and pass the context. We can get the arg types by mapping over term.args, and for each arg we will return type check helper on that arg and the current context. And what we need to check here is that we said our type checker needed to enforce that func type should be an actual function. If it's not, we'll throw an error and say expected function. We also need to check that the number of arguments that we're passing should match the number of parameters that the function expects. So func type dot param types dot length, if that does not equal arg types dot length, then we'll throw an error again and say wrong number of args. We need to check that not only is it the right number of arguments, we need to check that each of those has the correct type. So what I'll do is, we've already checked that they're the same length. So I can just, I'll just do a for loop here that goes over argtypes.length. And inside this for loop, what I want to do is say expected type is going to be the func type param types of I. The past type, or kind of the actual type that's given, is arg types of I. And well, we just need to check that this expected type and the past type should match. So if they don't, we can throw an error and say wrong arg type. If that all succeeds without any errors, we've checked that it's a function, we've checked the number of arguments, we've checked the argument types. So at that point, we can just return the return type of the function. So if the function returns an int and we're calling it, then the overall expression of the function, the overall type of the function call, is going to be that return type. Okay, so that actually handles all our cases besides list, which I said we'd come back to. So I guess let's go ahead and try running the tests here. You can do that by running dino test, and then the path to our test file is going to be test/test. So if we run this, okay, you'll see that we have some of them passing, but we have a whole bunch of them failing. So let's look at what some of these errors are. We get things like undefined variable plus, undefined variable minus, string length. So you might remember that I said plus is something that's in the standard library. String length is as well. And this kind of makes sense, right? We're trying to refer to plus from the standard library, but this function is only checking in the context. So what we should actually do is anything that's in the standard library is just kind of globally available to refer to. So I have this function here from the standard library that we can use to look up if this variable name that we're trying to get the type of exists in the standard library. So this just takes the variable name, and it'll give us back either a standard lib function or undefined. So we can say if it gives us something, if there's a standard lib result, then we'll return the type of that. Okay, so that should help with some of these tests. If we run the test again, then, okay, great. So we have a lot more passing now, 2 failures. And let's look specifically at those. So what we're seeing is that both of these tests that are failing are ones where I'm expecting a type error, but I did not get a type error. So let's actually take a closer look at the tests right now. The first one that's failing is conditionals with type n. So let me go to that one. And it's the one where I'm expecting a type error. And well, I guess I can just kind of spoilers. This is the specific test case that is failing. So the test case here, let's look at it specifically. We have a function call because of this open paren. The function that we're calling is defined here. So it takes 3 arguments, x, which is a Boolean, a function 1, which should be a function that takes 2 ints and returns an int, function 2, which also takes 2 ints and returns an int. And the body of the function just says, if x is true, return function 1, else return function 2. We're passing in a Boolean for x. We're passing in plus as the first function. That looks good because plus does in fact take 2 ints and return an int. But then we're passing string concat. And string concat is, as you probably expect, a function that takes 2 strings and returns a string. So we should expect this to have a type error. We should expect this to throw an error because string concat does not match this type. So if we look back at our type checker and kind of think about which case this is, the issue we're seeing is that, well, for one thing, the argument type does not match the parameter type. And this is actually a further problem, which is that the then type does not match the else type. So if we start out by looking at where we check that the argument type matches the parameter's expected type. Well, that was right here, right? We're looping over those arguments and the parameters and checking that their types match. But all we're checking here is that they have the same tag. And so plus and string concat, those do in fact have the same tag, right? Both of them will have the tag ty arrow for arrow type. So just checking that they have the same tag isn't actually, that's not quite enough here. We need to check kind of the all the things within there. So when we look at what a ty arrow has, it has param types and return types. We need to check that those things actually match as well. So I'm going to write a helper function here. I'll say like types are equivalent, and it'll take type 1, which is some type. It'll take type 2, which is some type, and it'll return a Boolean that says whether those 2 types are equivalent or not. Okay, well, we know right off the bat that if they have different tags, they're not equivalent. So we can check that and get that out of the way immediately. So if they have different tags, they're not equivalent. Okay. If we look at the types that we have, so Boolean and int and string, well, the only thing they have is their tag. So those just checking the tags is sufficient. List we're skipping for now. So let's handle this arrow type here. So just to satisfy TypeScript, I'll say if type 1 tag equals type arrow and type 2 tag equals type arrow. This is not strictly necessary because we already know that they are the same. I'm just doing that so that this allows TypeScript to infer that type 1 has these like param types and return types, as well as type 2, because it knows within this block both of these are the arrow type. So if they're both functions, they're both arrow types, then what do we need to do? Well, we said we needed to check that their param types match and their return types match. So this is sort of similar to what we did before, which is I'm going to check that they have the same length. same number of parameters that they're expecting. So if they don't, then this function returns a Boolean, so we'd return false. If they do have the same type or same number of parameters, then we can iterate over those and check that each one has the same type. So if they're not the same type, and I'm just going to use this function that I'm defining right here to check that they're the same. So type1 dot param types of I, type2 dot param types of I. Those are not equivalent. We can return false. And then we also have to check the return type. So if the return types are not equivalent, type1 return type and type2 return type, well, then we can return false as well. And otherwise, if we get through all of that, then they must match. So we'll return true. All right, so now that we've done that, I'll clear this and run our tests again. And, oh, well, I wrote that function, but I'm not calling it anywhere. So we're still getting the exact same test failing. Okay, so I said we needed to use it when we're checking here that the expected type matches the past type. So let me put that in. So instead of checking tags, we are going to use our function that checks that the types are equivalent. And I also pointed out in the tests that right here, we need to check that the then and else types are equivalent. So right here, we're checking that then type tag matches else type tag, but that's not enough because in that test case, both of them did have the same tag. They were both typed arrow, but we need to check that their types are equivalent. So we'll check then type and we'll check else type. All right, now that we've checked those, I will go ahead and run the test again. And this time they all pass. Okay, so that completes our version of the type checker that relies on type annotations in the program. So again, you'll see in all of our tests where there are functions, each parameter that the function has or expects has a type annotation associated with it. So in all of these, every time you see a function parameter, it's followed by a colon and then a type. Let's talk. I promised I would come back to this list thing. Yeah, let's discuss that right now. So we have this list type that we wanted to do, and let's say we wanted to write a function which takes a list and just let's do something super simple. A function that takes a list and tells you if it's non-empty. So if we do this and we say lambda list, and then we have to give it a type, and all we want to do is we just want to say if it's empty, we'd return false, otherwise we'd return true. Super simple function. I know you probably would never write this. Empty is built into the standard library, so you'd probably just negate this call, but let's write it in this format for now. So what we need to do here is we would need to provide a type annotation on this argument. So the type that we were expecting, again, back here is you do a paren and you say list of type. So we can do list of, but then what do we put here? Well, we could say like list of int, and then it would work as long as we pass a list of int. We could say list of string. That works for strings, but you're seeing the problem here, which is that it only works for like one specific type. We kind of want to say like a list of like T, right? And like have some sort of, like generics in Java or TypeScript, something like along those lines. We're not going to implement generics in our version with type annotations because it's what you might find is that this problem will, because we're going to do the inference implementation instead, you'll see how if we have type inference, what we can basically do is just, we'll in fact even leave off the type annotation completely, and it will just be able to infer what type to fill in there, depending on what you're calling it with. And it will even allow you to, in some cases, call it with a list of ints, and in some cases, call it with a list of strings. So right now, we aren't really quite able to implement lists in a very effective way when we have type annotations without generics. The other thing I want to mention real quickly is that I have some test cases here at the bottom which are commented out right now. And these are test cases that involve recursive functions. So if we try to run one of these right now with our program or our type checker as is, I'll run this. You'll see that we get an undefined variable type error. So if we go down and we look here, what's happening? Well, we have a let expression here that is creating the variable factorial. And then in here is this lambda. And inside there, we try to call factorial recursively. If we look back at our type checker and we look at this let case, the first thing we do is try to get the type of our value that we're assigning for this variable. So the very first thing we're doing is trying to get that type. And at that point, we're still using the old context. So the variable we're defining doesn't yet exist in the context. So when we're defining the variable factorial, but the first thing we're doing is trying to get the type of this lambda. And so if we refer to factorial inside there, it's going to say, well, that's not defined yet. I don't know what this is. We don't have a type for it yet. And so we run into an issue where it thinks that variable is undefined. What we kind of want to do is we want a way to like put that variable into context and say like, hey, this variable exists. And we just like, we don't know its type yet. Its type is to be determined, but it exists in the context. Right now, we don't have any way of doing that. We don't have a way of like representing a type that is to be determined. So with that said, that kind of leads us into our type inference section of the workshop. So this section just kind of goes over some of the things that I was just mentioning. Specifically, the two difficulties that we ran into were with lists and with recursive functions. So these are just, again, examples of how if we're trying to define like functions which use lists, we have to like only use a specific type. And with recursive functions, again, like I just went over, we need a way to say that this like variable should exist in context with a to be determined type. So there are multiple ways to solve both of these issues. We are going to focus specifically on solving them through a type checker that is able to infer types. So our inference algorithm will solve both of these problems because the way we're going to do this is we're going to have kind of exactly what I was saying we needed, which is a way of representing a type that is to be determined. And so that way, for lists, the programmer will be able to just leave off the type annotation, and the inference algorithm will just kind of say that it's a to be determined type, and it'll figure out when it should be a list of int, when it should be a list of strings, and so on. And with recursion, we'll be able to say, put this variable into context and just, give it a to be determined type for now, and we'll, determine that type later. So let's kind of go over the inference algorithm. The general idea that we're gonna be doing here is we're gonna do a pass where we kind of traverse the abstract syntax tree, and we're gonna assign types, and those we're gonna assign types for each node in the tree. If it's a Boolean or something, we can just directly assign type Boolean to it. But if it's something else, like something a little more complicated, an argument to a function that doesn't have a type annotation, we can just assign it a to be determined type. And while we're going through there, we'll just generate constraints that involve those types. So we can just generate a constraint that says, this first expression for the if should match a Boolean type. So after that pass, and I'll go through an example of this since that was probably, kind of abstract. After that pass, then we're going to do a pass that unifies those constraints. And so what we'll do is kind of just go through each constraint and process it. And I'll explain exactly, how that processing happens. And if we ever run into some contradiction, like a constraint that cannot be solved, Boolean should match int, that's a contradiction. Then we'll be able to throw an error, and we'll say that this program is not well typed, it has a type error. So I'm gonna actually go through the visual example first, and then we'll refer back to like this table while we're doing the implementation. But I think it'll be easier if we actually kind of go through this visual example. So the program that we're going to be looking at is the one I was showing earlier, and we're also calling it. So we're going to say let non-empty be a variable that has the value of this function, which is a function which takes one argument list. If it's empty, returns false, otherwise returns true. And then we're going to call non-empty, and we're going to call it with this list that has one element inside of it. So the abstract syntax tree for this program looks like this. So again, the root node is that let expression. The value is a function abstraction, has one parameter list. The body is an if. The condition is a function application, a function call, where we're calling the empty function. The then case is false. The else case is the Boolean true. And the body of our let expression is us. It's a function application term because we are calling that non-empty variable that we've just defined. And we're passing a function application where we call cons and pass it one and the empty list. So this is our abstract syntax tree. And let's go through, we said the first phase of the inference algorithm is to assign types and generate constraints. So the first thing to look at is the value of the let term. And when we look at the value, well, the value points to this function abstraction node. So if we look at that, the first thing we're going to do is say, well, it has one parameter, the list, and there's no type annotation there. So we're going to assign it this to be determined type, which I'm just going to call T1. Then we can look at the body. When we look at the body, that points at this if term. The first thing we can look at in the if term is the conditional. The conditional points to this function application. The first thing we can look at there is the function we're calling. And this function we're calling, empty, comes from the standard library, and the standard library will just tell us that that is an arrow type, which takes a list of T2 and returns a Boolean. So again, this is a to be determined type that's inside there because the empty function works on lists of any type. So then we can look at the arguments, and the argument that we're passing is the list, which is just referring to this parameter. And so we already have a type for it, T1, and so we'll put T1 here as well. And then the overall type that's returned by this function call, we'll just call T3. You probably are like, you might maybe are thinking that we could kind of reach in here and know that the return type of the function we're calling is Boolean. That is something we could do. The only reason we're not doing that is at this point, we're actually not even verifying that that this is a function type, which has a return type. We are just going to say that this is, we're not verifying that yet because that'll happen in the unification process when we check that the constraints have no contradictions. So all we're going to do is create a new to be determined type here and generate a constraint which will enforce that Boolean and T3 match for us. So the constraint that we've generated is that the function we're calling, this empty function, the type of that should match this function type where we pass a T1 and return a T3. Okay, that handles the conditional. The then is a Boolean, that's easy. The else is a Boolean. And so we know that the overall return type of this if expression is a Boolean, which means the body of this abstraction is a Boolean. So this is T1. This function abstraction is a function which takes one argument of type T1 and returns a Boolean. Then we can look at the body of the let expression. We have a function application here. The function we're calling is this non-empty function that we've just defined. So we know that the value of it has this type that we just determined, so we'll put that there. The arguments are this function application. The first thing to look at there is the function we're calling. That's T4, that's cons, which comes from the standard library. And we have a new to be determined type T4. So cons, again, it takes a new item to add to the list. It takes the existing list, which should match the types of the items in the existing list, should match the type of the item you're passing, and it returns a new list of the same type. And the arguments we're passing are int and empty. Empty is a keyword, like I said, that represents a list, an empty list of any type. So we'll just say it's a list of T5, and then the return type of this overall function call is T6. Again, same logic that I was saying over here. We're going to have this constraint which will enforce for us that this list of T4 and this T6 will match up. And again, same thing, a function call, overall type T7 with a new constraint. That Boolean will match T7. That means the body of our let expression has type T7, which means the let expression itself has type T7. So the overall type of our program will be T7, whatever T7 resolves to. At this point, T7 is to be determined. So whatever we resolve T7 to be is the overall type of this program. All right. So that was the first phase where we assign types and generate constraints. These are our constraints over here that we've generated. Now we're going to do the unification phase. So during unification, there's two cases to handle. One is where one of these cells is a to be determined type. If that happens, then we replace all instances of that type in the remaining constraints with the other thing that it should match. And then we set that aside as like a final constraint. Our final constraints will just be all of the constraints that tell us exactly what each of these to be determined types are. In the case where neither one is a to be determined type, we will just verify that the constraint is not a contradiction. We will deduce any new constraints that we can, kind of figure out from this one. And then, then we just remove it from our list because we're done processing it. So this first one here is an example of one that is actually neither one is a to be determined type. They contain to be determined types within them, but themselves are not to be determined types. So if we start going through this process, I'm just going to create this empty table here of our final constraints. And as a reminder, final answer is T7. So if we start going through, this first one here is case 2. Neither one of these is a to be determined type. It contains to be determined types inside, but themselves are not to be determined types. So we verify it's not a contradiction. Well, both of these are functions, and they both have one argument, so there's no contradiction here. We deduce new constraints, which are list of T2 matching T1 and Boolean matching T3, and then we're done with that one. This one is case 1. Because T3 is a to be determined type, we replace any remaining constraints that have T3, we would replace with Boolean, and then set that aside as a final constraint in this table here. Okay, Boolean, Boolean, this is case 2. We verify this is not a contradiction, and deduce any new constraints. Well, there's nothing to deduce here. Boolean matches Boolean, that's good. This is case 2 again. We have two arrow types. They both have 2 arguments, so not a contradiction. And we deduce 3 new constraints. T4 has to match int, list of T4 matches list of T5, and list of T4 matches T6. We're done with that one. This next one, again, this is case 2. We have 2 arrow types. They both have 1 argument, so there's no contradiction. And we can deduce 2 new constraints. T1 matches T6, and Boolean matches T7. Here, this is case 1, because T1 is a to be determined type. So we replace T1 in any of the remaining constraints with list of T2, and we set it aside as a final constraint. This is case 2, no contradiction, nothing to deduce, looks good. Okay, case 1, T4 is a to be determined type. We replace any instances of T4 with int and set it aside as final. Case 2, no contradiction because they're both lists. We generate or deduce a new constraint that int matches T5, and we're done with that. T6, this is case 1 because T6 is to be determined. So we replace T6 with list of int in the remaining constraints and set it aside as final. Case 2, and it's not a contradiction because they're both lists. Deduce a new constraint that T2 must match int. We're done with that one. Okay, this is a to be determined type. So we replace any instances of T7 in the remaining with Boolean. Well, there are none. We set it aside as final, and that one's done. T5, same thing, replace any instances with int. There are none. Set it aside as final, and T2. All right, so that finishes unification, and all that's left to do is we have our final constraints here. Every final constraint tells us exactly what our to be determined types are. So all we have to do is substitute these. We start at the top and work our way down, because you'll notice that it is actually possible for one of these to refer to some other to be determined type. But by starting at the top, working our way down, we would eventually, be able to replace this with an int in this case. So we just kind of substitute these in. We say our current result is T7. So we're going to substitute T3 with Boolean inside current result. Well, T3 doesn't actually appear in here, so there's nothing to do. T1 doesn't appear inside current result, so there's nothing to do. And we just keep going. T7, we substitute T7 with Boolean inside current result. Current result is now Boolean. And then T5, there's actually nothing to do. T2, there's nothing to do. And so our final answer is that T7 has resolved to type Boolean, and we say that our overall program is Boolean, which is in fact the case, because we call non-empty with a non-empty list, we're going to get back a Boolean. So this was our original AST, and everything has been replaced. I've just replaced those T1 through T7, and our final root node answer is Boolean. All right. So hopefully that helped kind of make some sense of this, how the algorithm will work. Now we just have to translate it into code. So again, this table is for the first phase. Based on the term we're given, we can assign it a certain type. And then I've written kind of the constraints that will be generated there. And then unification, again, it's the two cases that we just went through in great detail in that example. So with that said, I think we can jump into the code. If you're following along, you can check out the branch. I'm going to stash everything here, and I'll check out this branch, which you can check out as well, the 0.3 inference start point. That's where we're going to work from. So I also just wanted to show, I guess, and just to show what's on that branch. I just added a whole bunch of tests for our inference cases. So you'll see that like the equals function from the standard library, previously it only worked on ints. Now it's going to work on any types. This is just how I'm printing out a like a to be determined type. So equals can take any two. Well, it can take two arguments. Their types must match, but it doesn't require them to be ints anymore. And then some of the more interesting stuff, I guess, is I have a whole bunch of test cases where we're calling a function without a type annotation, and we'll still be able to infer the type of the the function and what it returns. So I've got a whole bunch, kind of the same tests as before, just without type annotations. Again, this is like the one that was failing. We'll see that we're still able to get it to correctly report the type error, even though we have no type annotations here. And you'll also see that we have our, just more without annotations, down here, these ones that were commented out, these recursive functions, we're going to be able to get those as well. So I have factorial, I have Fibonacci, and we also will have a whole bunch of test cases that deal with lists, because we're going to be able to implement those as well. So the rest of the changes in this diff are just kind of things to look at to enable the type inference. So I've uncommented these, the list stuff, because we're going to actually be implementing lists, and I've made the type annotations optional in the parser because the programmer is no longer required to actually annotate those. All right, so let's get into the implementation here. Let me close that. Okay, so what we've got here is this is the same function we wrote last time. So it's not, it's complaining right here because, well, it's complaining here because this type annotation is now optional, but we need context to, we don't allow like null types in our context. And then it's also complaining because we need to add cases for our empty term and our cons term. So I'm going to go ahead and, well, I'll just create those two cases here. I'm going to put them here. So empty, and I'll just throw an error here. And then cons. And as a reminder, cons has a, if we look at the parser cons, it looks like this. I'll just paste that in to remind ourselves. All right, so we said that our type check function this time is going to operate in a couple phases, right? We said the first one assigns types and generates constraints. So we're going to have, we're going to modify this function to not only return type, but it's also going to return us a list of constraints. So I'm going to just do that like that, keep things simple. You could probably, maybe organize this better. But I'll call that type and constraints. Like if you wanted this to be, an object or something, I'm just going to return a pair, type and a list of constraints. So Once we have those constraints, the next phase that we were going to do is we wanted to unify those constraints and unify those constraints. That will give us back our final constraint. So you'll remember that was the table where everything was the to be determined types. Every entry in there was one of those. So that'll give us our unified constraints, or our final constraints. So once we have those, then the only remaining thing that we did in that example was we just kind of substituted everything in into our result type here, and that gave us our final answer. So our final type is when I'll call it apply substitution into this type of our unified constraints, and then we can just return this final type. Okay, so we've got a whole bunch of stuff to do now. We need to change this function to give us back not only the type, but the constraints as well. And then we'll need to implement the unification process as well as our substitution at the end there. So let's kind of just adjust this. So when we see a Boolean, again, this case is very easy. And if we look back at our table, again, the assigned type is going to be Boolean, and there's no constraints to generate. So all I have to do is go like this and say empty list for constraints, and that's it. Same for ints and strings. And if we do those, okay, so those cases are done. Variable, we're still going to just look up the type in the context, and there's no real new constraints based on that variable. So yeah, we look it up in the context and no constraints generated. Okay, so empty. This represents an empty list of any type. So it could be a list of int, it could be a list of string, it could be a list of functions. So what we'll do is I'm going to create a variable for the element type, and this is going to just be one of those to be determined types. So what we can do here, well, it's not any of these, arrow, boolean, int, or string. So we need to, we're going to add in one more type, I guess. So we'll call this the TBD type, to be determined. And we need to give it a unique identifier. So in the example we went through, I labeled all of them like T1, T2, up through T7. In this case, a convenient thing that we can do within TypeScript is use a symbol. And so I have this genUnique type variable function from our utils file, which is going to give us back a symbol. So we'll call that whenever we need to create a to be determined type. So that'll be the symbol. So in here, we know that the element type for the empty term is going to be a to be determined type, and that takes a sim, and we'll generate a unique type variable for that. And that way we can return, so the type we're returning is a list type where the elements are, well, that element type, and no new constraints because there's nothing for us to say about that list. All right, cons. This one will have some constraints because we need to check that the type of the car should match the element type of the coder. So what we can do is we can say that we'll get the car type first, and we'll get whatever constraints are generated from recursively calling this function, get type of, and we'll pass term.car, and we'll pass the context. And then we can do the same for coder. So the coder type, and we'll say those are constraints 2. All right, so here's the the constraints that we're gonna generate. We're gonna have some new constraints, and those are gonna be we need to say that the Cutter type matches a list of car type, right? Just make sure I'm not getting that backwards. A list where the element type is car type. Yes. So that should match Cutter type. And then we also want to say that, actually, no, I think that's, yeah, that's the one constraint that we need here. So we have one new constraint, which is car type, a list of car type matching Cutter type. And then what we can do is return, we're returning a pair. So the type we're returning is Cutter type, because it's just going to be a new list of the same type as the old one. We could also put this in here because we have a constraint that says those are the same thing. It doesn't matter. And then the constraints that we're passing or returning are, while we have the new constraints, in this case there's only one, we have as well as the constraints that were generated when we did our recursive calls. So we should pass those through as well. So, all right, that finishes the cons case. We got the type of the car, the type of the Cutter, created one new constraint, and then returned the pair. Let's look at if. So I'm gonna go like this, actually. I'm gonna move those up and say these are constraints 1. The then type is constraints 2, else type, constraints 3. All right. Now, instead of directly checking this, at this point, we're not, again, we're not actually doing the checking. We're just generating constraints. So what we can do is say new constraints, which should be some constraints. And this time we have 2 new constraints. So we have that cont type should match, should be a Boolean. And we have that the then type and the else type should match. And that's it. And then we can return a pair. The type is, again, then type, else type is the same. That would also work. And our constraints, we can do the new constraints and then pass through our constraints that were generated in our recursive calls. So that handles the if case. Let, we can, so what I'll do here, I'm going to use some variables just to kind of make things maybe a little easier to read. So we'll say that's the body type. Let's say I'll get this val type outside just so it's a little easier. Something like this, where we get the val type, we get the body type with that new value in context, and then each of these can generate some constraints. These are going to return pairs again. Constraints 1, body type will give us constraints 2, and that way we can return a pair with the body type and constraints 1 and constraints 2. But I just want to go back to kind of what we said at the end of our previous type checker. So we were talking about recursion specifically, and we were talking about how, I mean, one of the kind of motivations for our type inference implementation was to be able to do recursion and to be able to say, this new variable name should exist in context when we're evaluating the value, so that we can say like let factorial, and then inside that function refer to factorial itself. So right now we're not doing that yet because we're still just passing the old context when we're getting the type of this value. So I'm going to create this TBD type which will have that tag and symbol, and this will be a new unique type variable. And what I'm going to do is then say that when we are getting the type of the value, we want to pass that in and not just pass the old context. So what I'm going to do here is, put this same thing basically. So we have a variable with this name, and this time the type is that TBD type. So here, the variable will exist in context with some to be determined type. That allows us to get the val type, even if that value refers to that variable recursively. We can then pass that val type into this recursive call when we're evaluating the body type. And then we just need one more constraint here. So in this case, our new constraints that are being generated, we need to say that this TBD type that we kind of said, hey, this variable that we're defining, it has this TBD type, that should match up with whatever we actually determine is the type of that value we're assigning to that variable. So all we need to say is that the TBD type and the val type should match. And then I'll just put that new constraint in here as well. So we have the new constraint that the TBD type and val type should match, as well as passing through the constraints that were generated from our recursive calls. So that should allow recursion. So that's one of the big pluses compared to our previous implementation that's been done here. Okay, function abstractions. So what I'm going to do here is we still have our params context, but it's complaining because null is not assignable to type. That's because our type annotation here can be null now, because we don't require the programmer to pass that type annotation. So we're making it optional. They can still pass it, but when it's not there, we will fall back to a TBD type. And the sim is a new unique type variable. So just by doing this, kind of use the type annotation if it's there, otherwise new type variable. That will give us our params context. And then what we need to do now is just change this to return the pair instead of the type. So we're still returning that arrow type as a type, and then constraints, well, abstraction, no constraints. No constraints there, and then let's fix this return type. So I'm going to move this out into a variable. Because this recursive call is returning the pair, it's not just the type anymore. So we'll say return type here, as well as constraints. And we don't have any new constraints, but we should still pass through these constraints as well. I guess I don't need to spread that. I can just pass that through. All right, so that should handle function abstractions. We are, assigning the to be determined types. That's the main thing here when there's no type annotation. And then last case again is function applications. So again, let's get the function type, and then let's get the arg types. Initially, we'll say that's empty, and then we'll kind of, we're gonna also be getting arg constraints each time we do the recursive call on the argument. So I'm just gonna use a for loop. For const arg of term.args. We'll go over each of those, and we'll say arg type, arg constraint. Oh, it's kind of awkward. I'll just do constraints one again, and say this is going to be get type of term.arg and context, and then oops, sorry, we're iterating over term.arg, so get type of arg, And then we'll just add those in. So argtypes, we'll push that argtype in there. And then we have our arg constraints. We'll push any constraints we get through in there. And oh, that's still complaining from down here. So once we have those, what we need to do then is we have our function type, our argument types, and then we'll do our return type, which is just going to be a to be determined type, which will have a new unique type variable. And again, we will have a constraint that this return type should match the return type of that function. So let's do those constraints now. Let's think about those. These are going to be what I said, which is we have function type needing to match. This needs to match an arrow type with the param types that it should match are the arg types that we're passing, and the return type should match that to be determined return type. Okay, so this is saying the function, this function type is kind of like what the function expects, right? And the arg types here are kind of what we're actually passing, and then the return type is going to be that to be determined type, which should match the return type that the function is actually going to return. Okay, so that's the new constraint that's generated, and then all we need to do here is we don't actually need to manually check this because we're just generating constraints. We don't need to check these. That'll happen. All those checks will happen later during the unification. At this point, we're just saying we just have these constraints that these things should match. And so what we can do is return a pair again. So our type that we're returning is still the return type. In this case, we haven't actually verified that func type is a function as an arrow type. So I'm going to just use our return type variable and then our constraints. So the constraints that we have are the new constraints that we've written, as well as all of the arg constraints that we got when we were recursively calling this function on our arguments. And was there anything else here? Yes, I just forgot that func type here is the pair. So this is also going to be, well, I've kind of messed up my numbering here. I have constraint 1 down there, so I'll just do constraint 2. And we'll pass that through as well, constraint 2. All right. Okay, so that should, I think, manage, that should handle all of the cases for the part where we are assigning types and generating constraints. So if we go back up to what we needed to do next was to unify those constraints. So let's write that function next. I'm gonna, well, I'll just put it at the bottom here. I'll say unify, and we get a list of constraints, and we're actually just gonna return our constraints. These are gonna be the final ones where it tells us like T1 is this, T2 is that. Each one in the final constraints that we return is gonna be one of those TBD types. So the cases that we need to handle here are the two cases that we went over in this type inference example. So remember here, we need to handle kind of the TBD types separately from when there's not TBD types. So what I'm going to do here is let me just Well, first let me just check that constraints. If this is 0, we'll just return empty. I just want to get that done kind of off the bat, because the first thing I want to do here is say type 1 and type 2 equals the first element of the constraints list. And then just for ease, I'm going to say this is going to be constraints.slice1. All right. So what we want to do is we want to handle, so if ty1.tag is this a TBD type, we also need to handle when ty2 tag is TBD type. The first thing I'm going to handle is when they're both TBD types, because in that case, what we want to check is that hopefully they should have the same, like if we ever run into like a constraint that says T1 matches T1, you know, that's good, because that wouldn't be a contradiction. And that is just, you know, we can kind of just process that, and there's nothing to deduce there. And so we can just unify the rest of the constraints in that case. Otherwise, let's do the case where T1, type 1 is that TBD type. So what we can do in this case is, let's look back. So we replace all instances of that type in the rest of the constraints, and then set this constraint aside as final. So what we're going to do is say our, like, I'll call them the replaced constraints, and this I'll make a function that says substitute in constraints, and we're going to substitute this symbol with type 2, because that's what it has to match, in the rest of the constraints. And then we will set this aside as final. So the way I'm going to do this is by saying ty1, which is the TBD type, this is our a final constraint. The rest of the constraints are not yet final, and so I'm going to do a recursive call to unify so that these are going to continue to be processed. So this is final and is going to appear in our actual return value as is. These are still going to go through the unification function. So that should handle, oops, that's pretty jump. That should handle that case. And then we kind of have the exact opposite case when if ty2 is the one that's the TBD type. So I can go there. I'm just going to copy and paste this. And now we just need to switch these. I'm going to switch these as well so that the TBD type is always the first thing in our final constraints list. And that handles those. And so then the else case is when neither one is a TBD type. So the way I'm going to do that is in here, and I'll say if, I guess the first thing we can check is that their tags should match. So if their tags don't match, we can throw an error. If they do match, then what I'm going to do is I'm going to kind of handle each case separately here. So I'm going to switch on the type that we need to handle. So let's do Booleans. And our Booleans, our ints, and our strings are actually going to be really easy. So let me just, these are the easy cases again, as usual. And then we'll have lists, which I'm gonna like that, and we'll have functions, which I'll go like that. And we shouldn't need to handle TBD type because we've already, you know, have the else if cases for those. So okay, so we've already verified that the tags match. So Boolean, int, and string. Well, otherwise verify it's not a contradiction and deduce any new constraints. Well, the tags match, so there's no contradiction. When you're matching a Boolean and a Boolean, there's no new constraints to deduce either. And so all we're going to do here is just continue to unify the rest of the constraints. When we have a list, so we have two lists here. What we need to do here is generate a new constraint that the elements in those two lists should match each other. So what I'm going to do is just unify, and I'm going to unify kind of the rest of the constraints. And then our new constraint here is that ty1.element type should match ty2.element type. And TypeScript is just complaining because even though we already checked that ty2 tag matches, it can't quite infer it. So I'm just going to throw this in here. It knows it matches ty1, and it knows ty1 is type list, but it doesn't quite take that extra step that ty2 is type list. So if I just throw this error in here, then it's satisfied. And it'll be happy now to say that both of these have the element type field. So that's our new constraint. We're going to continue the unification process on the rest, as well as this new constraint. All right. We have our arrow type. I'm going to have to do the same thing here to convince TypeScript that ty2 is also an arrow. And then what we can do is this unification process is where we're actually, again, verifying that it's not a contradiction and deducing new constraints. So to verify that this is not a contradiction, we know that they're both arrow types, but we also need to check that they have the same number of parameters. So if they don't, then I'm going to say there's an error. And I'll just say like contradiction, num params mismatch. And if they do, then we're going to create a new constraint for each of those parameters that they should match. So let me loop over those again. I less than 201 length. And let me just kind of, let me do this. New constraints dot push. So we're going to have ty1 dot param types of I should match ty2 param types of I. Okay. We have all those, and then we also need one new constraint for the return types matching. So ty1 dot type 1's return type should match type 2's return type. All right, and then we can just kind of continue unifying the rest of the constraints along with our new constraints here. All right, so that should handle that case. So the one thing we skipped over was this part where we're substituting in the constraints. So this unification process is done. We've handled the two cases, which were the TBD types, where you substitute it in the rest of the constraints and set it aside as final. And we handled the case where neither one is a TBD type, where you check that there's not a contradiction and deduce any new constraints. So let's do this function where we substitute in constraints. And this took the symbol that we're substituting for, it took the type, and it took the constraints that we're substituting inside of. And it's going to give back new constraints where that symbol has been replaced. So what I'm going to do here is just map over those constraints. And for each constraint, I'm going to take off each type. So type 1, type 2 equals constraint. And I am going to just kind of return, substitute inside the type. And I'm doing this because we're also going to use this substitute in type function when we do our final substitutions at the end. remember with like per result being T7, and then we substitute in all of our final constraints. So we'll reuse it there. So substitute in type sim type in ty2. And so that'll give us back a new type and a new type here. So this will be a constraint, a pair of two types which must match each other. So if we write that function now, we have our symbol, we have our type that we're substituting it in, and then we have our our type to substitute inside of, I guess, and it will give back a new type. So in here, I'm gonna do kind of a switch on our type. So I'm just gonna copy and paste this so I don't have to type that all again on each sort of type that we have. And this is going to be, we're going to switch on the type that we're substituting inside of. So if it's a Boolean, an int, or a string, and you're trying to, substitute for any occurrences of this symbol inside there, there's not going to be any occurrences of that symbol inside Boolean since it's string. So we can just return that. If you have a list, what we need to do here is we still are going to return a list, but we need to replace any occurrences of that symbol inside the element type. It could be the element type directly, it could be nested within the element type. Type to substitute inside of. We need to replace the symbol inside there. I can delete all that. If we have an arrow type, again, we're still going to return an arrow type, but we need to substitute inside any of those param types. So param types will map over them. For each param type, we can return substitute in type, and we'll pass the same symbol, the same type, and that param type. And similarly for the return type, we need to substitute inside there. So we'll go like this. Substitute in type, sim type, inside that return type. Okay. And then the last case is the GBD type. So this is where the actual substitution happens. So far, we've just been doing the recursive calls. We haven't actually made the substitution. So here's where we do that. So if you see something, if we call this and say, hey, replace T7 with Boolean inside T7, that's where you actually make the substitution. So if type to substitute inside of, if its symbol matches the symbol that we're trying to replace, that's when we return this type. If they don't match, replace or substitute T4 with Boolean inside T7. Well, those symbols don't match. So that's still, you don't change anything. You keep the type to substitute inside of. It's only when their symbols match. That's when we do the substitution. Okay. So let's see. That should handle our unify function. The last thing we need to do is to substitute each of those constraints from our final unified constraints into our final type. And because we have that helper function, this is actually going to be quite simple. So this took the type and it took the constraints. These are the final constraints. And it's going to return a type. What we're going to do is I'm going to say let current result be that original type. We're going to return that current result at the end. And we're just going to go over each of the final constraints in that list of constraints here. And I'm going to verify, I'm going to pull off the two types. So TBD type should always be the first one. And then the other type is the second there. So I'll pull that off. I'm going to just throw an error if TBD type.tag does not equal TY TBD. We'll throw an error. It should always, first one should always be that TBD type. And then what I'm going to do is here reassign current result to be the result of substituting in the type with the TBD type symbol, the type that it should be, inside what is currently our current result. So that satisfies that. That finishes the implementation. The one thing that I just am going to point out now in the interest of time is that in these two cases, all we need to do is we also need one more check in here. So if the ty1 tag is a TBD type, we need to check if ty2.tag, well, what we need to check is that there's no circular references. So if ty1 is a TBD tag, we need to make sure it doesn't like occur within type 2, ty2. So if you have something that's like, you know, T4 should match list of T4, that's going to be a problem because there's that circular reference there. And so again, sorry about this for the interest of time. What I'm going to do here is we have this occurs in function that I'm just going to put in. So what this is going to be is checking if this symbol occurs in some other type. And this is very similar to our substitution, where we just, you know, for these simple ones, it's false. For the list and arrow, we just have to check these, you know, kind of sub types inside, the element type for the list, the param types for the arrow, return type. And when it's a TBD, that's when we'll check that the symbols match. So with that helper, we just need to check that circular reference case here. And so I'm just going to do if occurs in this symbol, if that occurs in type 2, I'll throw an error that says circular reference. And similarly down here in this other case, with the exact opposite. All right, so that'll prevent circular references. And with that said, we have now implemented the function that assigns types and generate constraints. We've implemented the function that unifies those constraints to get us our final constraints. And then we just substitute in to get our final type. And so once we've done that, let's try running the test. Moment of truth, and they all pass. So you can either trust me, I guess, or hopefully, if you're interested, maybe take a look at this test file and kind of play with some of these examples of programs and, you know, try and, you know, like modify them and see if you can make things fail, see if you can, you know, verify that the way it's inferring something will work. Just, you know, kind of to look at some of the more interesting ones again. We have the test case for factorial, where, and I can even remove this annotation and still run the test and everything should pass, where we're defining a variable factorial that refers to itself, and we're down here, we're even using it. So, you know, factorial of 4 is 24, I guess. And we have some tests for lists as well, that can handle, you know, multiple lists. So in this example, we have a function which takes some argument x, and we're able to call it with we're able to call it I guess here with both kind of lists of ints. You know, you can kind of go through these. There should be some where we're calling a function with ints, and then later in another program, another test, we call the same list function with a string. Yeah, list contains here, I guess, is one example of one that should work like that. So yeah, with that said, hopefully you were able to follow along here and kind of work through how the type checking algorithm works. Thanks so much for joining this. I know I'm just a few minutes over here, so I guess I'll kind of wrap it up there and leave it at that. But we were able to get through both the type checker that relies on type annotations, as well as a type checker where it is able to infer all of the types for the entire program. So again, thanks so much for joining. I hope that was enjoyable and maybe learned something or had fun implementing the type checker. All right.